might not have, either because you're on the first section of you're just beginning your design, and then your airplane is still not mature and you don't know everything about it, or maybe you're trying to model an existing airplane with not that much information, like it's going to be our case with a military aircraft not having every single thing published. And as we were saying, which military aircraft we're going to model, it's going to be the one from the Italian Frecce Tricolori. It's the aerobatic demonstration team from the Italian Air Force. You probably know the ones in the US, the Thunderbirds or the Blue Angels. And the airplane that they use is the Aermacchi MB339, a two-seater advanced jet trainer. Let's go to System Modeler and let's see if what we are saying is true. And we'll be able to model this airplane in less than 20 minutes. Right now, we can just return to System Modeler. And the first thing we're going to do is create a package. This, think of it as a folder. It won't have spaces. So here is where we're going to store everything that we're going to be doing today. Even though you can start from zero and from scratch to model your own airplane, the easiest way to go, and which is what we are going to show today, is to just drag and drop an existing airplane. In this case, you can see in the physical, the fixed wing. Here are all the airplanes that we have modeled for you. So one of them, it's going to be the general aviation aircraft, which is kind of like a standard small size Cessna. And then you're going to put it over here in the aircraft webpage webinar package. We're going to rename the copy because it won't longer be a general aviation aircraft, but Aermacchi test.
So is that a model that which, let's say, is it a reference model which we can change the parameters? You said that we model some airplanes for us. So
yes, that is correct. There is a base model, let's say it like that. And then you're going to be changing the parameters. For example, for the Boeing 737, we already put some of the parameters to actually make it work like the 737. The same is for the DCA, the Pipistrel Alpha Electro. We have electric airplanes. But right now, what we're going to do is drag and drop, as we did the general aviation aircraft, and modify these parameters. So instead of being a general aviation aircraft, it becomes the Aermacchi MB339.
Okay, now I see. Yeah, thanks, Eric.
Awesome. No problem. So now let's see. You don't need top secret information to start. What we're gonna do, I'm just gonna put the system modeler here on the right. The screen might be a bit tight, but of course it's easier if you have a two monitors. The Wikipedia entry for the Aermacchi should be enough. So that means if we go all the way down to the specifications, here we have everything we need to first begin the simulation and get it up and going. Of course, the more precise information you get into your model, the more reliable your results are gonna be. Right now, I am just showcasing that it's easy to getting started using really, really top level information. So let's start with the mass. It's reporting 4,400 kilograms. And then the initial fuel. It's reporting, let's put 1,413 liters. If you use the density of the Jet A1, then you can get the mass, which I already did. And that's around 1,130 kilograms. Now, this is something interesting. The center of gravity position on the x-axis. If you know a bit about airplanes and their stability and control, you know that this parameter pretty much defines the stability of your airplane. That is why it is here on the general tab. It's going to be difficult to know exactly where it is just using the blueprints because there is no weight and balance sheet for this airplane. Nonetheless, we could assume that it's somewhere around on the quarter of the Mach. That is, if the wing has this chord, which is this length over there that I am showing, at 1/4 of it, that's going to be close to where we think the center of gravity is going to be. Of course, if you have better information, go ahead and use it. Another interesting thing that we need to consider is that what is the reference for this coordinate? If we go here to the introduction, we will see that it's not the center of gravity. This is because the center of gravity might be moving because our model can capture the fuel consumption. So instead of using the center of gravity, we use this thing called the fuselage reference point, which is a point in the middle of the fuselage if it was a cylinder. Usually, if you use your conventional tube and wing airplanes, it's going to be quite close to the center of gravity. And if not, you might have to do some algebra to just get it. But that's basically what we have. And so right now, we're going to put it somewhere around 30 centimeters in front, since we can see on the blueprints that it's a little bit close to the center. So 0.3. We also don't want to make it too stable because, of course, it's a military airplane that's going to be performing maneuvers. Again, as you saw, there is not that much precision in the way I got the center of gravity. If you have a better way, just go ahead and do it. The number of engines, it's just one. It's not engine mounted, so we leave that as false. And the engine type, if we see here, it's the Rolls-Royce Viper turbojet. So we go over here and we see that the turbojet is the number 2. Nice. And now it comes the geometry. Maybe the geometry is not going to be explicitly here, but this blueprint is all we're going to need. What we're going to do is we're going to open this web page over here, which is called laif.net, and we're going to upload this blueprint. What's going to happen is that when we give a measurement, let's say this one over here, and we leave it as a master on 10.97, all the other lines that we trace are going to be measured kind of scaled. This 10.97, we get it because we know that its length is 10.97. So, for example, if we want to get its wingspan, I'm not going to consider the wingtip fuel tanks, which the aerobatic version doesn't have. So that's going to be 10.08. Of course, if you have better blueprints, again, a better CAD, you can, of course, make it in a much better way. The wing root chord is going to be 2.5. The tip chord, 1.67. For the horizontal tail, its span, it's going to be 4.29. Its root, it's going to be 1.44. And the tip, it's going to be somewhere around 0.66. This one is also quite important for the stability analysis. So this one is going to be somewhere the distance between the fuselage reference points, so really close to the center, all the way to the leading edge of the horizontal stabilizer, which is going to be something like 3.22. Negative because it's going towards the tail. The vertical tail geometry, it's going to be really similar as the horizontal on 1.73. Its root, so the one closest to the fuselage, 2.09. And the tip, 1.25. Nice. And now it comes to the aerodynamics, specifically for the wing. This one, you can get it, for example, here it's going to tell you what kind of airfoil it's using. The airfoil is the shape of the wing. And you can, of course, get this from airfoil tools. You can perform your own analysis using maybe Xfoil, maybe panel methods, whatever you want. The sky is the limit on how precise you want to get this information. If not, or you might not even have an idea of what this means, that's perfectly fine. The only thing you're gonna do is just like it is right now, you leave the default value, which is showed here in gray. And if there was something written for this particular airplane, which was a general aviation aircraft, we will just delete it and we leave the default value. In this case, 0. So we're assuming it's a 0 lift angle of attack of 0, so asymmetric airfoil, which it's going to be kind of close to where we want for this aerobatic airplane. And this 1.5, let's see what we have as default. 1.2, it's going to be your CL max. So for those of you familiar with aeronautical engineering, might probably recognize that these numbers are like, okay, you know, a standard accepted estimate that you can get on the literature. And last but not least on this tab, we're going to do the initialization. We're going to make it fly at 20,000 feet of altitude. And by that, I'm just going to click that. And with the new unit handling version, we can just forget about annoying conversions. For example, what is the initial velocity meters per second? I have no idea. But I know that, let's say 800 kilometers per hour, and that will automatically convert that. That's it for the general tab. If we go to the mass and inertia, we're going to have to make its moments of inertia, because of course, on a 6 degrees of freedom rigid body, that's the thing that's going to dictate how it behaves. And I'm sorry to tell you, but there's no easy way to calculate these moments of inertia. There's no just a magic formula that will get it for you. It's something that you kind of need to go through. There's a lot of methods that you can follow. For example, there is one with the Wolfram language in which you can import a CAD figure and it will give you the moments of inertia. That's how we did it. I will not show it because, of course, it's not in the scope. You may have found the information on some specifications in the internet, or maybe you have your CAD that might give you that information. And if all of that fails, you can just go back to the common aircraft design books and you will have some nice correlations there, maybe using the Raymer as we do in aeronautical engineering studies. So these numbers that I already have, I will just write them down. 6, 9. And of course, these are also approximations. Don't think of them as completely perfect. And 8,005. Nice. And then we'll just build the main diagonal of the tensor. Everything else, we'll just leave it on 0. We also have a weight estimation method that you might want to try and test. That's quite interesting too. Right now, we are not using it, so we leave it on false, and all those parameters, we don't worry about them. Now that we have this, if we go to the other tabs and leave everything as the default values would ask us, your airplane should be good to go. Of course, with all the assumptions that you might have. You know, everything here, let's just return it to its default value. This is kind of like the magic and why it's quite easy for beginners, because you don't need to know every single thing of your airplane. But of course, we today have some extra information that we might want to fill. Maybe we don't have the main root thickness, but if we assume it's around 13% of the Mach, those of you with aeronautical background, you'll know it is kind of there. For example, we know that the wing has some lambda, you know, so we can just put some 30 degrees over there. It has a tiny bit of incidence that we can see over here, so it's around 3 degrees. Of gamma, not incidence. It's dihedral. The horizontal tail also has some 30 degrees of sweep. Let's put it over there. And the wing reference area is actually given here on Wikipedia, 19.3. This is a very important parameter, so if we have it, we might as well just use it. For the vertical tail, let's use also the lambda on 30 degrees. And we have more information about the fuselage, so let's just use it. The 10.97 that we were discussing. The width, we can get it from, again, our little web page, 1.13. And the height, we can also leave it on 1.55. If you don't have this information, just leave it on default. And if you don't agree with me and believe that the values that I am putting are really low quality, then be our guest, download the library and put some perfect and very precise values. And then you can demonstrate, of course, that your simulation will run a lot better. Well, it will be more precise, actually. If we go to the aerodynamics tab, this airplane calculates the drag at every single interval using the drag buildup method. If you are not familiar with that, it's kind of approximating the shapes of the airplane to some known drag coefficient values and just adds them up. So of course, there's some form factors that you might want to change, some skin, how coarse is the skin of your airplane that will define your skin friction. If you don't want to deal with that right now, you just leave it on default. If you have very good information about it from another program, just fill it yourself. We need to know the limitations of the model. This airplane is giving you some aerodynamic information to work, and also as a reference, but it's mainly for looking at its rigid body dynamics, not so much for doing aerodynamic simulations and results. For that, you have CFD, the panel methods, and you name it. The control surfaces, for example, for those of you who are not familiar, are the little flaps that move either here and here and here, and that the pilot moves to control the airplane. Those are designed usually later on the design stages. So maybe at first you might not have them. So you can just leave it as they are right now, all in gray, all in default. It will place them somewhere, you know, kind of where it's agreed they should be, with some deflections that might work, at least for the first initial testing. And finally, in this page, if we go to the initialization, if you're going to show this simulation, maybe you're going to present it in a colloquium to your superiors, to your classmates, partners, you want it to look nice. And you also want to get some insights on the animation. So we're going to put it on true. And the CAD path, you can have your CAD as long as it's .obj stored somewhere. Right now, I have this path just saved over here. And I will put it here. You can either put it here directly or open it so you can actually see it complete. Good. So it looks okay. Now that we have nothing else to here, the last thing that it's missing, it's just the motor, the engine, the propulsion system. We're gonna redeclare the component to one of the existing ones that we have, either turbofan, turboprop, and all the others. In this case, we said it was turbojet. You saw all the other ones that we have. And so for the engines, if we just put one that we also have preloaded, that should be enough. For example, it's a turbojet, we'll just use this Pratt & Whitney JT4. If you have a better model of your turbojet, go ahead and use it. Maybe that's your main interest, like the propulsion plant. If not, just use one that it's uploaded over here. And just like that, I believe the airplane is already modeled. How much did that take us? I don't think more than 20 minutes. And now the only thing that we need to do is to place this model in an actual significant environment. For that, I already prepared this. And we're just going to put it here. And this is the nice thing. This is the airplane that we just did. We're just going to drag and drop it over here. Just like that. And then we are going to connect it to the inputs that later on I will come back and explain them a bit. And now that everything, of course, it's only one engine, so the thrust input is just going to be 1. And we're going to rename this so that it works with the plots that we have over there. Aermacchi test. And we're going to see, 15 seconds. It's going to be enough just to see how it flies. Awesome. Now let's start the simulation. And while it simulates, I'm going to come back and explain a bit what these things that I connected are. This is just a constant source. Nothing elegant, nothing impressive. It's just a 0-degree angle for the ailerons. The ailerons are the ones that control the roll. For the elevator, we just put a tiny bit of a negative deflection so that the airplane is a tiny bit up and it doesn't go down so fast. The rudder, the one that moves the airplane like this, is going to be on 0. And this thrust over there, imagine as if it was the pilot's input on the throttle. So from 0 to 1. So this would be something like 70%. Now, if we go back to our system modeler, it did simulate. So it worked. We simulated it in less than 20 minutes. Here we have the altitude and the airspeed, of course, growing because there is no pilot on board, right? We just connected some constant inputs to this. Let's see how does it look. Here is the airplane. And then if we, of course, we put it a bit fast. Now we see some of the forces generated on the wings. And of course, it's going down because there's no pilot over there. And you can, of course, plot a lot of things. For example, the drag coefficients that it might be estimating. You have both the induced and the parasite one, which, of course, this airplane going so fast, the parasite is expected to be the largest one, and the total drag coefficient. This should not be considered as completely precise because, again, this is not an aerodynamic simulation. But just like that, you can plot and get information about a ton of elements that you might want to plot, including fuel consumption, the load factors and stuff. But now that you saw that it's possible to model your airplane in 20 minutes, let's do something fun with it. Right now, we just got it flying and that, but we want to see aerobatics. Right, Vedat?
Yeah, exactly. Maybe Eric, before going on to the fun part, Carl is asking questions related to Reynolds numbers, and he is asking, out of the full-scale aircraft, do the models allow simulation of RC fixed-wing aircraft with the appropriated Reynolds numbers for small wings? So, do we have any comment on that?
Definitely. Yes, Carl, thanks for the question. You can, of course, simulate your small RC airplanes. For example, I would recommend just using the Pipistrel Alpha Electro, which is already electric. And then you're just going to make it small of size. The Reynolds number at which your airplane is going to be operating will be deducted by the simulation once you give them the speed and the size of your wings. So that's perfectly possible if you are into RC airplane flying, maybe like you. But yeah, awesome. Yeah. So yeah. Of course, now coming back
also allow us for the low Reynolds numbers, right? Low Reynolds numbers airfoils.
Yes, of course, it depends. You cannot really get into like when the Reynolds numbers becomes tricky. You know, if you want to capture the transition and all this stuff, this model is not for that. It might give you some insights, right? But you need to know your limitations. But yes, as long as you're not trying to do something outside of the period of the validity of a normal airplane, you know, if you want to try to simulate an airplane that's this size, maybe that's going to be quite weird because then the Reynolds numbers behave weird. But if you try to do a fixed wing airplane 1 meter of a span or the way to the jumbo jet, you should be on the safe side.
Okay, yeah, thanks for that.
Nice, no? Awesome. But now that we're speaking about that, the forces in equilibrium, on the straight and level unaccelerated flight, for those of you who are not that familiar with the forces in an airplane, the lift, the force produced by the wing, is opposing the weight, and they are in equilibrium. And the thrust, which is going forward, produced by the engine, is opposed by the drag, the force of the air that is trying to make the airplane not move. This is very nice and things, but it only happens in straight and level on accelerated flight, not in aerobatics. When we're flying aerobatics, then we actually have some things called G forces. Maybe you've heard this in some of the, in even the popular culture. And these are some accelerations that affect both the airplane and the pilot when you are flying in maneuvers. And they are measured in G's, which is the acceleration of the Earth's gravity. And when you have a high G feel, you feel as if an elephant is sitting on top of you, as if you're being pushed down to your seat. When you have 0 G, that we have heard probably, it's as the astronauts in the videos that we see on the ISS and etc. And when you have negative G's, which is my personal favorite, it's similar to what you feel in a roller coaster drop. So instead of being pushed towards your seat, you feel that your struts are the only thing keeping you there. I write as my personal favorite because I used to be a pilot and I used to love making this negative G's maneuver. They really feel really weird. These are measured by this thing over here called the load factor, in which is the relationship between the lift and your weight. And while your weight remains fairly constant, not considering the fuel burning and stuff, the lift is actually changing. And let's see how does this look in the pilot's point of view. This is the Saab Jazz 39 Gripen, designed and built here in Linköping, where I am speaking from, by Saab. Now you see why we had a collaboration with them in creating this aircraft library. This G meter on the pilot, who is actually an astronaut who just returned to Earth, we see that just by turning your airplane, the pilot and the airplane are feeling 3 Gs of acceleration. So pull down into your seat 3 Gs, 3 times their own weight. And this one is on the loop, on a pull up. Not only happens on turning, but when they are pulling up, we'll see at the beginning of the GIF that the pilot is gonna push the stick up all the way to 9 Gs. That's really close to the structural limit of probably from the Gripen. That's the pilot feeling 9 times its own weight. And then in the end, a little bit of negative Gs. So pushing towards its belly of the airplane. So how do we know that we are not stressing the airplane as I was speaking, that we are flying inside the permitted zone? We use the Venn diagram, and this thing relates the velocity on the x-axis to the load factor in the y-axis. So we can see that this one, which is an approximation to the Aermacchi one, it has a positive limit of 8 Gs and a negative limit of -4. This is interesting. It's not symmetric. Both the airplane and the pilot can withstand better positive Gs than negative ones. We'll see why that's important in a bit. These straight lines are determined by the structural limitations from the structure department, the same as this never exceed airspeed. You cannot just dive on your airplane and go extremely fast and not expect anything to happen without messing with supersonic and compressible flow things. And these ones curved over here are the aerodynamic limitations, in which if you are going too slow and you are weighting 4 times your weight, your wings won't be able to support you any longer. This is, of course, an oversimplification, but let's go to model this high G aerobatics in System Modeler with the airplane we just did. Right now, I have this aerobatic show prepared for you with 5 airplanes. The first one is just going to be connected to an autopilot. We have a collection of autopilots that you can use and you can try to use for your own airplane. If hopefully one of them will fit just right. If not, you're going to have to tune it. And just like with the moments of inertia, there is no easy escape from tuning and autopilot. But nonetheless, if it's quite conventional, you can just do it. Or if you're even better and you really like control, you can design your own autopilot and test it here. This is your altitude and track and velocity. So this autopilot is mostly used like for navigation. Let's call it like that. And maybe if you don't know how the autopilot works or what tuning an autopilot is, you can even go simpler. For example, over here, I have the split S maneuver. The split S maneuver here shown on the Aresti symbology for aerobatics. It's showing that the airplane starts over there on the little circle. It makes a half a roll, and then it turns back 180 degrees from when it was facing. These maneuvers were, of course, used a lot during the first years of World War I and World War II pilots in dogfighting. And don't think that there's anything complex inside this. It's just a pulse. It's just a pulse for the aileron and for the elevator and a constant signal for the rudder and the velocity. It's nothing out of this world. You go ahead and do it. It's really easy. Of course, if you want to create your own autopilot for performing aerobatics, be my guest and we will be quite impressed. Here we have the split S bad brother, the evil twin, which is the English blunt. Here you're doing exactly the same, but instead of turning at first, you are going down on the belly of the airplane. Therefore, you are pulling negative G's. And this we can see on the diagram because of the dashed lines. And then once you pull all the negative G's and you're in the end, that little arrow shows us we do a half a loop. And that's how we end up just like on the split S. The roll maneuver, you have probably seen it on the movies. It's quite straightforward. It's just using your ailerons to roll on top of your x-axis. And this one over here, we'll just be able to see the first half of it since it's quite difficult to model only using pulses, which is the loop. Because the airplane at first is going to gather some energy by going down, and then whoop, it's going to try to go up all the way up into its space of least energy, which is going to be all the way here on the top. It's kinetic energy. But too much talking. Let's see how does this look actually.
Yeah, exactly.
That's
Show
right.
us some animation.
Now I can just leave it to your imagination. Or let's see how does this look
You
in
better not.
In the animation. Here on the aerobatic show, I'm just gonna close this over here. Let's see how it looks. Nice. Now we have our 5 airplanes, and for this I will put it on full screen. And let's see which one we're gonna follow first. Nice. So the split S. So you saw at first it does its half a roll, and then it's going downwards to finish up 100 degrees from where it was facing at first. That's from the split S. Let's see what goes on for the other maneuvers. The double roll. This one you have probably seen it on the movies. Top Gun fans. I am one. Of course, they're just gonna do it. It's mostly for spectacles, and there's not that much usefulness on doing that during a dogfight. If we go to the evil twin of the split S, which is the English blunt, let's see what this airplane does. So instead of making the half turn that we were looking, it's going all the way onto its belly. That's pulling a lot of negative G's. And you see why this maneuver is not that much done during air combat or during demonstrations, because the pilot cannot see where they are going. Imagine here on the cockpit, if I am going where my finger is pointing, I cannot really see it. Whereas if I am doing this, I can just turn up on the cockpit and see where I'm doing. And situational awareness is king every time that you're flying. Let's just see the beginning of the Q loop. I will put some velocity on this one since it's a bit more slow. At first, it will dive a bit to get some energy, and then boom, a sudden pull on the controls to take this airplane all the way up, all the way to half of the loop. At that point, the pilot needs a lot of power, but once it reaches the top of the queue, it needs to leave all the power because it has a lot of potential energy to change. And finally, the one that might seem a bit more boring is just the autopilot, which we'll see that it's actually working. We see, yes, so this one is just flying normally. We see that at first there were some oscillations that we'll dig a little bit into that. And this looks pretty, but let's see what actually information we can get from this simulation. What can actually make it worth to do it, other than just looking pretty? We can plot, for example, the load factors over here. Here I have the one from the split test, English blunt, and the double axial roll. For the split test, we can see that actually we are exceeding the limitations because the limitation should be somewhere around here on the 8 or something. So for a tiny bit of moment, we are exceeding these G's. Probably not a problem because it's not for that long and it's not for that much. Nevertheless, on the English blunt, remembering that our structural limitations was around -4, which is somewhere around here ish, we see that it's really, really pushing it. So this maneuver, as it was simulated, should not be done. The double axial roll, for example, we see that the loads are not going that much. It's not that bad. We are never going over 2. And we also see the load factors for the autopilot. At first, some oscillations. This is expected because you're initializing your airplane already flying. And then you're going to have some oscillations that in the end will just fade out. And we have a little bit of negative G's because in the end, once the airplane has reached its altitude, boom, it just corrects down. When it comes to the Q loop, this one definitely exceeds the limitations. We see that the pull-up maneuver, this peak, just hitting the yoke so fast, it goes all the way to almost 12. So definitely this maneuver could not be approved. Or I'm not saying the airplane is just going to disintegrate in the air, maybe, but probably not. But definitely it's going to have to go into some maintenance programs that are going to be they're going to cost a lot and things. So the simulation can tell you this kind of information. And that's pretty much what we wanted to show to you today. And we open the floor for some questions.
Yeah, Eric, thanks for this nice and cool presentation. I just want to ask a question related to NV diagram. I am just a newbie regarding the aeronautical. So you said that we have this NV diagram. So where does it come from? Is it something like, assume that you mentioned the Swedish Air Force, right? Gripen. I mean, we saw so many Gs over there. Is that they have some certain maneuvers while they're training themselves and they went to manufacture, I don't know who those guys are, and ask for that kind of airplane? Or is that what the manufacturer can do and the Air Force are limited to those boundaries?
Yeah, definitely. It depends. Usually on the case for civil aviation, if you want your airplane to actually be certified under some regulations, for the example, the FAR 23, FAR 25, they are going to tell you, your airplane must be able to withstand +4 positive Gs and -2, let's say. And then the whole design team is going to have to design the structure and all the systems surrounding the structure to comply with this limitation. And in the end, some tests will be given and they will say, okay, it does comply. And this is the Venn diagram that will be published in the pilot's operating handbook, for example. In the military area, it might be a bit different. Maybe, as you said, the Swedish Air Force, for some reason, has the need of withstanding 12 Gs. And they need that's their like the upper limit of the Venn diagram. So probably they will publish, we need a new fighter jet that withstands 12 positive Gs and -6. And then, of course, there's some kind of bidding and these really, really complex things going on. But then the designers will actually try to achieve this using structural design. So this is not something these limitations are given, as I was saying, by the structure department. So they make their own tests, in which you are very familiar with that, with structures with that, to guarantee that the airplane is going to be able to withstand either the certification for the civil part or the specification that the Swedish Air Force is asking. And then the same, they will just publish it on the pilot's operating handbook for the pilots, and they will make sure not to exceed it. Of course, now there are computers and things to make sure that it does not exceed, whereas before, on World War II, it was the pilot that had to kind of feel that they were not exceeding the Gs or pass out.
Oh, we have even such risks. Yeah, you're right. Yeah, I have never thought of it. Yeah.
Nice. Good question.
Other than that, we got question related to is there any way to get those inertia tensors by using Mathematica? Right, as I said, as I answered on the chat. So yeah, we have a way to do that. You can use create system model. In that one, it takes in as long as it's in region. You can just specify your region. It can be in CAD shape, or let's say in STL, and it might have some data within, like the density and such, and then you can have it. So, and then you can create a system model object out of it. It will be a 6 degrees of freedom object in system modeler with all the inertia tensor values, matrix values. So yeah,
Exactly.
it is easy thing for Mathematica users, I would say.
Yes, and that's
Other
really
than
nice
that,
that we can couple, as you were saying, Vedat, maybe you are very interested in what we show today, which is the 6 degrees of freedom rigid body dynamics. But maybe you are very interested in, for example, you have a very nice model of a hybrid electric propulsion system, like the one I did for university. And it's quite nice there, already working by its own, but it would be interesting to put it on this airplane and for example, simulate a whole mission. Or maybe you are more interested in actuators, and then you'll be able to modify the actuators of the control surfaces. So basically, this is an open canvas for you and for the specialization that you want to, and the level of depth that you want to put on your model on whatever you're interested for. That's what the system modeler can offer you with all the libraries in electrical, mechanical, and stuff. So it's up to you how far and how precise you want to get the simulation.
yeah, great. Yeah, thanks for the nice explanation. And we have two more questions over here. And Jörg is asking, I assume that he's from northern countries, not so sure. Is it possible to simulate airplanes with delta wing configurations in the current library? Right.
In the current library, right now, no. Right now, you know probably that they actually generate lift in a kind of different way. So just the way that they are right now, no. We are actually planning on developing on that and adding some other stuff. For example, the Delta Wing, some canard and stuff. And if you really cannot wait, you can of course dig into the library, go into the wing, see how it's modified, how the lift is generated, the equation, and modify it for the delta wing that you wish, which is something that we did, for example, on a previous tech talk of Wolfram, when we simulated the speed of sound and the drag that it generated just using some world forces. So currently, no, expect it soon. And if you cannot wait, you can, of course, do it yourself. It's quite easy.
Yeah, another question related to air pressure, humidity, and temperature. So you show that our airplane just increasing in altitude, and doesn't change any type of drag and lift and etc. So do we take into account all those differences?
Yes, yes, definitely. As it's commonly done on the industry and in academia, we this library has the standard ISA atmosphere. So the more up you go, the colder you get. Probably when you are flying, you see on the window of your airplane these tiny ice crystals that begin to form, and this of course modifies the lift and the drag, because the colder it gets, it modifies the density, but also going up in the atmosphere, there is a bit less air, so the density is modified. This model does account for that using the ISA function as usual.
Mm-hmm.
Of course, you can implement other atmospheric, more advanced models. And depending on your focus, you could even make use of the fluid library and really get an air model that's really, really, really precise. If you are trying to get other things, for example, humidity, for example, I don't know if there is dust and stuff, how all these
Mm-hmm.
things that modify slightly your lift, drag, and forces production.
So what you are saying is that when it comes to fidelity, sky is the limit.
Exactly, Vedant. That's correct. That's it. And it all depends on your model. A single model will not be able to answer all the questions. It depends on what question you're trying to ask. As I was saying, if you're interested in power, in propulsion, electricity, and that's where you can give it. This model is for you guys to really set free your imagination and make it as precise as you want.